This week and what we're doing in lab today, we're going to be doing a dry lab today. And so what this deals with is now looking at the specific structure of atoms. What are atoms made up of? How do we know what atoms are made up of? And what atoms are made up of? And the structure of how they're made up of those constituent parts, how does that relate to chemical and physical properties? Right, so elements are the primary substances, which all other substances are made from. So originally we would say that elements cannot be broken down into simpler substances, and for the purpose of chemistry they really can't, right? You can't take a hydrogen atom, go through a chemical reaction and convert that into a helium atom, for example. However, if you start getting into the realm of nuclear physics and stuff like that, you know, what's happening at the center of the sun is actually refusing hydrogen atoms to form helium atoms. But for chemistry purposes, we're not worried about them changing identity and stuff. Why? Because we're going to be worried more not about the structure of the nucleus, though it is important, but rather the structure of the electrons around the nucleus. And so these elements usually have names that are derived from their Latin names, right? So uranium, the planet Uranus. You have titanium, the Titans from mythology. So a lot of elements are named after that, or they can be named after what they were, or who they were discovered by, or where they were discovered, right? So we have californium and then berkelium, which were both discovered up in Berkeley National Labs in Northern California. And so a lot of these names, you know, a lot of, you know, classes, they'll have you kind of memorize all the different elements on the periodic table. I find that usually the best way to do it is, like, even if you memorize them this semester and you go into your next semester of chemistry, you'll forget everything that you memorized this semester, and really just kind of comes with practice of doing this a lot, right? So it's useful to know all the names of the atoms, and if you do feel it will speed up your understanding of a lot of this stuff, but it's not something that I'm going to be explicitly testing you on. However, I do want you to be able to look at elements and then look at the periodic table and then find those elements on the periodic table and why they're at that specific spot. Okay, and so how do we symbolize elements? So usually they're 1 or 2 letter abbreviations, mostly 2 letters. Only the first letter of an element symbol is capitalized. If the symbol has a second letter, it's always going to be in lowercase. And the reason we distinguish things that way is because these 2 symbols here have completely different meanings, right? So this is, especially in intro chemistry, a mistake that happens a lot, is the lowercase. So this O is lowercase, whereas this one is uppercase. This one is lowercase. The first symbol there represents the element cobalt. This is an element, meaning that it has an identity associated with a certain number of protons and electrons. The second symbol there, right, so they're both capitalized, and we'll get into this probably next week. Does anyone know what that might symbolize when we have 2 capital letters next to each other? It's a compound or a molecule, right? So this is going to be carbon monoxide, right? So we don't have a single element anymore. We have 2 elements that are going to be bonded to each other, right? So that's why it's important to distinguish between the capital and lowercase letters, especially when we get to writing molecular formulas. So this is important for molecular formula. So when we look at the periodic table, and we'll talk a lot about that today, what the periodic table is and why it's organized the way it is, those are all going to be elements. When we're looking at chemical reactions, though, we're going to be mixing elements and molecular substances. So it's important to distinguish between them. And cobalt is one that makes sense where that name comes from, right? CO, cobalt, that kind of goes hand in hand with each other. Some other elements is just going to come from using them a lot, where you're going to get there. Where they get their name from is usually from Latin words. So on the next slide here, am I good to go on? I still see some people writing. So the next slide, we have Na, which is for the Greek, interpretation of this element. Does anyone know what Na actually is? Sodium, right? So this is sodium. Iron is Fe, or ferrum is the Greek name for that, right? So a lot of these, they don't necessarily make sense because we don't speak in Latin or Greek, but that's where the elemental symbol comes from. That's because a lot of these things were used before we had the specific study of chemistry. Again, I'm not gonna have you guys memorize all the names, but as you especially once we get into the nomenclature of ionic and covalent compounds, it'll be important to be able to distinguish that, right? You have to know what the element name is to actually give the molecule a name. And then we've also mentioned this before, that some of these elements in their natural form, they don't exist as single atoms, right? So we talked about an elemental molecular compound. These would be the elemental molecular compounds. These only exist as diatomics, right? So H2 is going to be hydrogen, O2 is oxygen, nitrogen is N2, iodine is I2, bromine, Br2, chlorine is Cl2, and then fluorine is F2. So these are naturally found in their diatomic state, meaning that they're bonded to each other when you find them in nature. You will never find a single atom of hydrogen floating around unless maybe you're in the deep, deep vacuum of space. But most likely, even wherever that hydrogen is made, whatever star it was fused in, it will find another hydrogen atom to form H2 relatively quickly. Right. And so these are called diatomics. What do you guys think the prefix di means? Two, right? So that means two. And once you get into naming molecular compounds, well, you'd be using these prefixes a lot, right? So di meaning two, atomic just means two atoms. And so how do we organize all of these elements? Well, we do in what we call, and what you guys see everywhere in this building and in this room, in the periodic table. And so the periodic table, right, is a logical organization of these elements. And kind of the whole focus of today is how do we organize the periodic table? And there's some things that are going to be related to properties of a compound. So what we're looking at here is a breakdown of 3 different classifications of the type of elements that we have, and other ways that are more related to the atomic structure of all of these elements. So everything that you usually have in blue here, this part of the periodic table, these are called metals. And we'll talk about what a metal means. It's related to how easy or hard it is for that substance to give up an electron. The yellow are going to be nonmetals. So most biological life is composed of these elements, and usually just these 4 right there. Those are going to be our nonmetals. And then in between these, we have a special classification of elements. These are called the metalloids. And I don't really need you guys to memorize all of them. The important ones here are really just going to be a couple that we mentioned, right? And so this breakdown of the periodic table isn't based off of the atomic structure of these substances or these elements, but rather their physical properties. However, their physical properties do come from their atomic structure, right? So you do see that there is a pattern, right? Like the lower left-hand corner of the periodic table, right? So that'd be things over here like francium, cesium, and stuff like that. Those are all metallic, and as we move towards the upper right, things start to become less metal-like. We reach this region where they're kind of in between a metal and a non-metal, and those are called the metalloids. And so what are some of these properties? Well, metals, these are going to be mostly solid. They're going to be shiny in appearance. That has to do with how they interact with light. They're good conductors of heat and electricity. So we talked a little bit about that last week when we were talking about thermoelectric devices. They're malleable and ductile, which is why they're used for wires. One, because they can conduct electricity well, and then also because they can be molded into things like wires. And in general, they lose electrons. We'll talk more about that in a little bit. Nonmetals tend to exist in all three states. They have generally a dull appearance, or if you made a powder of them, they would be opaque in nature. They tend to be poor conductors of heat electricity, although a lot of modern science is looking at making conductors out of plastics. So does anyone have the Galaxy phone, or not the Galaxy, the Samsung phones in here? Right. Is that the Galaxy? Yeah, so you know there's the Galaxy, and then they have the Z Fold and the Z Flip, right? So oh yeah, there you go. So you see how our phone folds like that? So that's actually a specific example of a nonmetal being, made into being a good conductor of electricity, right? So they use organic compounds to then conduct electricity and allows you to have a touch screen that's foldable there. So that's maybe a more antiquated way of looking at nonmetals, because a lot of modern science does change that. And if they're solid, they tend to be brittle. Obviously, they've solved that issue there as well, right? Another example of that would be polymers, right? So anything that's made out of plastic these days, you can think of some plastics that are hard and brittle, but other ones that are very flexible and rubber-like, right? And so those tend to gain or share electrons. So the bonding behavior of metals and nonmetals is going to be different. And this is getting ahead of ourselves a little bit, but these are generally going to form what are called ionic bonds, and these are going to form covalent bonds. But these are some general properties of metals, right? So this would be kind of like a multiple choice question on an exam would be, okay, if we had this substance and it's shiny and it conducts electricity, how would you probably classify this material? Yeah, right? So you would say that it's a metal, right? Or if it's dull and it's opaque and brittle, then you would say, okay, that's most likely a nonmetal. All right, and then we have the metalloids, and so these are going to have the properties of both metals and nonmetals. And so that can be useful, for example, if you want something to be covalently bond, so it'll have some flexibility to it, or can polymerize. But you still want to maintain some properties of metals, right? And so the most important metalloids that we have are going to be silicon and germanium. And those are important. Does anyone know why we use those a lot? Because they're in computer chips, right? So these, especially there's a lot of talk about computer chips in the news and stuff these days, because these factories that make these computer chips, they get silicon and they purify it to 99.99% pure, right? So the third decimal place. And they basically make these giant crystals out of them, and they're slowly pulling them up. So it takes a lot of money to be able to make these setups or these vats to make these giant silicon crystals. So that's why sometimes a computer chip factory can take upwards of 10 years to make. And so the reason that they're used is because you can what's called use photolithography, which is you use lasers and stuff to actually build transistors on the computer chips. And that has to do with the fact that these are both metal-like and non-metal-like, meaning that they can kind of conduct electricity. So if you add enough voltage, they can conduct electricity. But if you don't, then they won't conduct electricity, right? So this is how processors are made, right? So they're made from these metalloid materials. And those are usually, they tend to be shiny, right? So if you look at a computer chip, the material the chip itself is made of tends to be shiny because it's metal-like, but it can also be a little bit flexible, like a non-metal. All right, so those are some of the properties of the ways that we can classify the three different classifications we can have for elements on the periodic table. And these are related to their physical and chemical properties. But then the periodic table is actually more a hierarchy of how things are arranged based off of the atomic structure of them, right? And so these are based off of the structure of the electrons in the atoms, right? So the columns, right? So the columns are vertical. These are called the groups. And rows are called the periods, which is where we get the name, the periodic table. All right, so these here are the periods, and going this way, we have the groups. And so the only weird thing for the groups and some of the periods is that this whole region right here, which will come up with a name for that region, those we don't include in the groups. So the way we number the groups are we have group 1, 2, 3, 4, 5, 6, 7, and 8. And what this has to do is it has to do with the structure of the outermost electrons of these atoms. And so we'll talk more about what those electrons are and how they're organized in those groups and why we don't consider the middle ones. The periods are numbered normally. This is going to be period 1, 2, 3, 4, 5, 6, and 7. And that's going to be, bless you, that's going to be related to the maximum energy level in the structure of the atom. Right, so the groups are going to be related to electrons. Periods are related to the energies. And so there's some common classifications for the groups. And again, these are related to the energy levels of the atoms, which is what the periods are, and the groups are related to the valence, or going to be, that's what we call the outermost electrons. We'll go over that again in a second. But there's common names. In the center, that area that we ignored for the groups, these are called the transition metals. These groups 3 through 6, they don't usually have a common name, but usually we call them main group elements, or sometimes you'll see that they have no common name. Group 1, these are called the earth metals. Group 2 are called the alkali earth metals. Group 7 are called the halogens. Does anyone know what group 8 is called? The noble gases. The periods don't have any common names for them, as they're just related to the energy levels. These ones have common names for them because properties about them were determined before the discovery or the creation of the periodic table, right? So they already kind of classified these elements based off of things like reactivity. And when they organized the periodic table, they found that, okay, the atomic structure is related to their properties. All right, any questions on that? I know right now we're just kind of going through a lot of definition. We'll be applying it shortly, how these definitions are related to the structure of atoms. Okay, so actually let's take like a 6-minute break. So at 2:33, 2:35, we'll start again. And we'll continue with how is this related to early concepts of the atom. So we're going to build up early concepts of the atom into the modern concept of the atom. And then we're going to we're going to end with periodic trends, or how is that related to the periodic table. So let's go ahead and continue. So early concepts of the atom are by a guy named Dalton, and he basically said that each element is composed of indestructible particles called atoms. And these atoms of a given element are similar to each other and different from one another, right? So this seems relatively straightforward. Maybe if you were a philosopher at the time, you would have thought the same thing. And these atoms, they combine in simple whole number ratios to then create compounds, right? So back then, they really couldn't tell exactly what an atom was, but they could say, okay, if I know I have a certain amount of these two things that are reacting with each other and I get a certain amount of substance, that there has to be some ratio of how these things are combining with each other to then form the new substances, right? So that's what we mean when we say whole number ratios. And so these ideas are still, with us today. We still have the name atoms. The substances, or what they're indestructible, is not really true anymore, right? We just talked about how atoms are made up of different particles, right? But the whole number ratios, that's something we still look at today, because we still look at something called stoichiometry when we start looking and analyzing chemical reactions. So right now we're just talking about just a brief history of how we came to the modern idea of the atoms. So as science does, time progresses, new information, new experiments are developed to then modify existing theories, to then build upon and get a more complete picture of what's actually going on, right? So the first discovery was by a guy named J.J. Thomson, who performed experiments to look at subatomic particles, right? And these were also these particles that he found were negatively charged, right? So around 1897, this is about 50 years after Maxwell, the famous physicist who came up with our theories that are still used today for electromagnetism. So once electricity became more widely available, he's able to design an experiment that showed that there are particles smaller than atoms called electrons, right? So this led to the discovery of electrons. And so this discovery of subatomic particles, right? So the way this experiment worked is that we had a vacuum pump with some sort of halogen in there, and halogens, if you put them in a vacuum and excite them, you heat them up a lot, they start emitting electrons, right? So what they have is they have this cathode tube, right, which kind of looks like a neon light. Once you have a small opening, it allows for the emission of some of these electrons right here. And you put it inside a magnetic or an electric field, and what that does is it affects the electrons that are going through, right? Saying you have some charge here that's actually interacting with this field, and so the beam deflects when that happens. And so that deflection of the beam, especially towards the positive side of this electric field, tells us that there's something negatively charged in these atoms. And so what happens is then we take our previous version of this indestructible concept of the atom and we modify it, saying, well, now we know we have electrons in there, which means that they have to be incorporated in this model somehow, right? And so the idea, or the early idea, was that we had these indestructible particles, but basically it was comprised of something called electrons, and they were in a uniformly positively charged sphere, right? So this was kind of a jumble of just constant positive charge and electrons that are in there to kind of balance that out. And so it's kind of a mix. And so what this was called, it was called the plum pudding model, right? So the plum pudding model said we had a uniform charge, positively charged sphere, and then all these negatively charged electrons. And as it went through that electric field in the cathode tube, right, it polarized this a little bit, and if you had a lot more electrons that had mass on one side, then it would deflect the particles in the beam. Or the electrons could be completely kicked off of this uniformly charged sphere, right? So we say, okay, well, since this interacts with things electrostatically, there has to be positive and negative charges, right? So these are, at this point, fundamental properties of of nature, right? About 60 years earlier, that's when Maxwell came up with the idea of electromagnetism. So electricity and stuff was kind of known at this time, but what the interplay between electromagnetism and atomic structure was not known at all. So this was a very novel idea at the time. And so the plum pudding model, though, doesn't take into account the specific atomic structure. And so what happened was that in 1910, right, so the more advanced experiments are possible now. We can make different particles by exciting things in different ways. A guy named Rutherford, he further probed the nature of the atom. And in these experiments, what he did is he bombarded a thin sheet of gold, right? So a thin sheet of gold, things are bonded to each other with what are called alpha particles. And if we get time to talk about nuclear decay and stuff, we'll talk a little bit about what alpha particle is. Basically, what an alpha particle is alpha particle is a helium atom with a positive 2 charge. Right? So alpha particles are used a lot. Anything that does alpha particle radiation has a very, very short range, but can be very damaging because of how positively charged it is. If it gets near your DNA, it'll just start ripping off all the electrons of your DNA. And so what he did was he had an alpha particle source, and he sent these alpha particles the same way in the cathode tube, just a little opening that allows them to move in one direction towards this gold foil. And what he found was, or what they expected, was that if we had all these uniformly dense charged spheres just with electrons there, that goes in there, they're going to just start deflecting in all different directions. But what he actually found was that a whole bunch of the particles made it through. So this, big thing on the outside here, this right here, is just a giant detector, right? All it did is it just detect whenever a little charge hits it at some point. So a lot of them went straight through, most of them in fact, but every now and then you would get one that bounces in a different direction or in an odd direction. And so what was happening was that, some of the alpha particles are being scattered. And so what this said is that, well, the majority of the space in the atoms, if most of them are going through, has to be largely empty, right? So there has to be mostly nothing there, except very infrequently we're hitting something that's very dense and dense enough to actually deflect these charged particles. So that means that it has to, have mass, right, because it's deflecting it. And most likely it also has to have charge, right, based off of the degree of the deflection. If you have two positively charged things that comes very close to each other, what happens? They should push away from each other, right? If you ever take two magnets and they have the same pole, magnetism and electricity are very, very intimately related. It's kind of the same idea. Two magnets of the same pole, you push them together and they want to go apart from each other. And so what this led to is the idea that, well, the atom probably has a very dense positive core, mostly open space, and then negative charge that's kind of orbiting, right? So we still know we have the negative charges from Thomson's experiment, and now Rutherford's experiment says, well, we have the positive charge, but it's not just a uniformly positive sphere. It's very dense because most of the time when we're shooting it with this radiation, most of the alpha particles are going directly through. And so the model of the atom was then changed to what we call the modern structure of the atom, which is that the nucleus is going to be composed of positively charged protons in a very dense core, right? And so if we look here, we see 10 to the minus 10 is about the size of an atom. This is what we call an angstrom, so that's a symbol for an angstrom, right? So we have, meters, millimeters, micrometers, then we go down to nanometers, right? That's where things start to get funny in the physics world. And atoms are about 1/10 the size of that, right? So 10 to the minus 9 is a nanometer, 10 to the minus 10 is a angstrom, is how we define that. And that's about the size of an atom. And we see that the space that's the atom exists in is about 10 to the minus 5. But the nucleus, based off of Rutherford's experiment, is something like 10 to the minus 15, right? So this is about 10,000 times smaller than the size of an atom. So if you think about this in terms of scale, this nucleus is about the size of a football inside a football field if the football field is the entire size of the atom. And probably closer to the size of not the football in the field, but a SoFi Stadium, right? So that's how empty the space is most of the time that things are operating. This lets us, gives us intuition how strongly electrostatics come into play when we're looking at atomic structure, right? Everything is determined by electrostatics. We're going to talk about things called intermolecular forces, and they're going to have all these special names, but really all it is just positive and negative charges that are interacting with us. So that's why chemistry in general is determined by electrostatics. And so this nucleus is extremely dense, right? It has almost the entire mass of the atom, which is what Rutherford explained, inside this large negatively charged cloud where the electron exists somewhere. And most of the time, it's not able to interact with anything really. And so what he also found is that the masses don't necessarily add up to each other, right? So we have protons that account for the charge discrepancy or how they deflect based off a charge, but there's also the mass aspect of this. So there has to be something else in the nucleus that doesn't affect the charge at all. And so the nucleus is also composed of not just protons, but neutrally charged neutrons. And if you guys go farther on into physics and you're very interested in that, you'll learn that even those have subnuclear particles that make up those individual subatomic particles. And so this highly charged, positively charged nucleus, very, very dense, is surrounded by the electron. Let me write this better. The electrons that move rapidly throughout the majority of the volume of the atom, right? So most of the space, that physical matter we think of, is occupied usually by empty space, right? Only about a tenth or 1/10,000, not even 10,000, 1/100,000 of the space that we have an atom in our body is actually occupied by anything physical. Most of the space is just created by repulsion between electrons and stuff, right? So when you bring your hands together, what's actually happening is signals in your brain are reading a pressure that's exerted, but that pressure is actually exerted by the electrons in one hand repelling the electrons in another hand. Really, theoretically, your hands should just be able to move through each other based off of how much space is actually available there. It's really just electrostatics that are saying that they can't move through each other. And so this was then the revised version of the atom, right? So this is how we think of the atom currently in terms of its structure, but there were also still some things that had to be resolved in terms of this structure. The three subatomic particles, again, were the proton, neutron, and electron. The relative mass, meaning if we consider the mass of an electron like 1 gram, the mass of a neutron and a proton are about 2,000 times larger than that, and then they each have a charge associated with them as well, right? So proton, easy to remember, proton positive, neutron neutral, neutron should not have a charge, and then the electron is going to have a -1 charge. And so usually, again, how these are symbolized is proton is positive, neutron is going to be something like that, neutral, and then the electron is going to be something like that. That's usually how we symbolize it. When I abbreviate the electron, a lot of times what I'll do is I'll just write E- like that. But that's how we symbolize these different subatomic particles. And how do we use this then on the periodic table? Well, the periodic table, depending on what type of periodic table you look at, they're going to be slightly different from each other, is the large X here, that's the chemical symbol. This will be like CO for cobalt. For example, that gives us the identity of the atom. The mass number, A, that's going to be equal to the number of protons plus the number of neutrons, right? Because the mass isn't just given by the protons. Rutherford's experiment said that it's not just charge that's deflecting things, it's also mass. And then Z is going to be equal to the number of protons. And so this is the standard designation for a symbol, especially if we're looking at things like isotopes of different elements. On the periodic table, a lot of the times what you'll see is you'll see a square like the element up there. So if you look at that periodic table over there, you see bromine, right? The symbol is going to be in the middle. The atomic number is in the upper right-hand corner. And then the mass number is going to be below the element. And it's not going to give you a whole number because, again, we're going to have something else that we're going to talk about in a second, which are going to be isotopes, which mess with the mass a little bit. So this is going to be more what it looks like on the periodic table. And one thing about atoms is that Z is the number of protons. But what do you guys think about atoms? Do you think atoms are neutral, or are they going to be charged naturally? So they're actually going to be neutral. So if atoms were charged, what would happen is everything would always be reacting and moving around, and you would never have anything that's stable. So because we have matter that's stable and it's not decaying and going to something else, that tells us that most atoms are going to be neutral, right? So if we have a symbol like this, right, where we're told the mass number, the atomic number, the number of protons, how do you think the number of electrons is related to anything here? How do you guys think the number of electrons are related to any of these quantities? Using the fact that matter is neutral, right? Matter is neutral. Right, that means there's no net charge when we say that something's neutral. It means that we have the same number of positive charges as we do negative charges. So how do you think that's related to something here? Anai?
Would it be the number of atoms minus electrons?
The number of the mass numbers, you mean?
Yeah.
The mass number? So if we look at the mass number and we minus the number of electrons, the only thing that would be hard to determine from that is that we're looking for the number of electrons.
Oh.
Jaden? Yeah, it should match Z, right? So Z is our number of positive charges, right? So if our stuff is neutral, that means we need an equal number of negative charges. Where do the negative charges come from? From our electrons, right? So Z is also equal to the number of electrons in neutral matter. And I say in neutral matter because naturally atoms are going to be neutral, but in certain environments they can be and will be charged. All right, so if we look at the periodic table, we see lithium, which is atomic number 3, or Li. The atomic number, Z, is 3, which tells us we have 3 protons. But that also means for neutral lithium, then we have 3 electrons as well. And so this is our notation for the structure of atoms based off atomic number and mass number. And we can have things called isotopes. And so these are going to have the same atomic number, meaning that they're going to have the same number of protons, but a different mass number. And these are going to be called isotopes. So isotopes are really important for a lot of medical processes, a lot of different types of imaging. So for example, if you want to look at how old a rock is, or an old skeleton or fossil, you can date that fossil by looking at the decay of an isotope of carbon, because you know how much it decays, and how much is there. So you should know how much of each isotope that you have. And so what does that mean? If we have a different mass number, but the same number of protons, well, the only way we change the mass is by changing the number of neutrons in the substance, right? So here we have 3 different isotopes of hydrogen. We have just regular hydrogen, or protium is what it can be called. Or sorry, this is protium, which is going to have 0 neutrons. So it's just a single proton and a single neutron. Then we have deuterium, right? So now we still have the same single proton, right? Because all isotopes have the same number of protons, same electron, but now we've added a neutron to the hydrogen. And then tritium, which is going to be another isotope of hydrogen, same number of electrons, same number of protons, because those stay the same, but different number of neutrons, right? So the mass of these has changed. And so if we look at the different elements here, we see the different symbol that tells us, remember up here we have the mass number, right? So mass number of 2 tells us that we have 2 massive particles, it's either protons or neutrons. This tells us the atomic number, which means that we only have 1 proton, so that means you have to have 1 neutron. And that also tells us the number of electrons. And same thing here. So because we have a mass number of 3 now, and a atomic number of 1 still, the difference between the mass number and the number of protons gives us the number of neutrons, right? So 3 minus 1 is going to give us 2 neutrons that are left in there. And what we should start thinking about is, well, if these have the same number of protons and the same number of electrons and just different masses, then what does that tell us about what protons and electrons and how they give us the properties of the materials? And so what we'll find is that the protons give us the identity of the element, right? Because it's related to the atomic number, which goes up as we go across a period on a periodic table. And then the electrons are going to kind of give us the personality, right? How does this thing interact with other things? And so the mass of these atoms are all measured relative to some chosen standard, right? So when we think about our standard SI units and stuff, we have something similar for atomic masses. So everything's really compared to a standard carbon-12, which is an isotope of an atom, all right? So if we have the name of an atom or an element, a dash, and then a number, that number tells us the specific isotope. And these masses are expressed in atomic mass units. Right, or just abbreviated AMU. Right, so when we look at the different masses on the periodic table, those are going to be expressed in atomic mass units. And we'll get into how are those related to macroscopic masses like grams and kilograms. And so because each element can have multiple different isotopes found naturally, they're going to be weighted essentially by their abundance. So that mass that you see, so remember I said that the mass number isn't given to you in a whole number on the periodic table. It's because it's an average of all the masses of the isotopes. And so these are weighted according to their abundance. And that's just a fancy way of saying that, well, they're just weighted by how much we see each type of them, right? So if we see protium more than deuterium on the previous page, that means the mass is going to be closer to that of protium because that's way more abundant in the universe. And so the mass of an element is closest in value to its most abundant isotope. Right, so we'll use this as an opportunity in an example or two for how we can calculate averages and things like that related to percentages or how abundant something is. And so let's look at an example here. Right, so here we have an isotope of chlorine. So if you're given this atomic symbol, what are the number of protons, electrons, and neutrons in this chlorine atom? Right, so that means we want to find Z, A, and the number of electrons. Bless you. All right, so what's one thing you can look at this immediately and tell the number of? Yep, we have A, which is the atomic mass, and that's equal to what? 35. And what else? Z, which is what? 17, and that's equal to the number of protons and electrons. So then how would we use this to get the number of neutrons in our substance? Yep, you subtract Z from A, right? Because A is equal to number of neutrons plus Z, right? So if we want to solve for the number of neutrons, subtract Z from both sides. That gives us A minus Z is equal to the number of neutrons. So 35 minus 17 equals 18. All right, so we should be comfortable looking at a symbol, an elemental symbol, and determining what isotope it is, how many electrons there are, and how many protons there are, and how many neutrons.